Go ahead and get started. So I want to welcome everybody to the November 2019 Staties webinar. My name is Martin Beziner, and I'm the Director of Research and Development at Staties. And today we're going to be talking about DOE, Design of Experiments for Binary Data. We have a pretty good sized group today, and so that we could keep this presentation somewhere in the 35-minute, maybe 40-minute ballpark, everybody's going to be muted. So if you talk, I can't hear you. However, you're more than welcome. If there's something that's not clear, or if there's some question that you'd like me to answer, you can go ahead and feel free to email me at this email right here. Let me go ahead and just get my pen. You could go ahead and email me here, martin@staties.com, and I should be able to get back to you later today. And this presentation will be posted online on our website probably by tomorrow. So the slides as well as the video will be there. So what are we going to be doing today? Well, first, I'm going to start with a simple introduction to what is binary data. This is a topic that we run into quite often. We see that people have binary data often, and yet they don't necessarily know what tools they should be using to set up experiments and analyze the data they collect. So I'll go through an introduction just to kind of make sure everybody's on the same page. Afterwards, I'll go through two simple examples. So a response surface example as well as a mixture experiment. Later, I'll talk about some tips and tricks that you can use when you're off on your own designing experiments for binary data. There's lots of resources available, lots of books, lots of articles available on how to analyze binary data. There's not nearly as much about how to set up the actual experiment. In other words, how to choose what runs you're going to be doing. Knowing ahead of time you're going to collect a measure a 0, 1, or yes, no, or any other type of binary response. And then I'll kind of wrap things up, give you some resources, and then send you off for the day. So why don't we go ahead and get started and just introduce this problem here. So in a typical DOE sequence, you would first start off by choosing your factors or your mixture components. And then what you need to do is choose the lows and the highs. You need to figure out, any constraints that involve more than one factor or more than one mixture component and so on. And all of these together are going to define what's called the design space. This is the region where you're going to be performing the experiment. Now, in our experience, probably about 90% of the, success, whether the biggest factor, probably 90% is of whether an experiment is going to be successful is whether you define this design space adequately or not. Most of the time when we see an experiment fail, it's because people are experimenting in the wrong space, they've chosen the wrong factors, the wrong components, and so on. Afterwards, you can use software to generate the actual experimental plan, the experimental design here. Okay, then you go off and perform the experiment. Once you collect the data, you can build a predictive model. You could build a predictive model that takes, that it's basically an equation where you put in your factors and it gives you a prediction for what it thinks the response is going to be. This is typically done using ordinary least squares, at least in Design Expert. If you've always done the analysis of variance, it uses ordinary least squares regression in the ANOVA, possibly with a transform if there are problems. Afterwards, once you have your predictive model, you can optimize, figure out where's your minimum, where's your maximum, where's your sweet spot. Okay. Take that sweet spot and confirm it. Do some independent validation runs afterwards just to make sure that your model is agreeing with what's actually going on. And then finish, and then possibly, go back if you need to any of these steps if something goes wrong. Now, what is binary data and why is it special? Well, in most cases, industrial experiments are going to have responses that are continuous, and those can be analyzed using ordinary least squares. So a continuous response, it's one that can, in theory, take any value in some feasible range. Okay. Of course, I say theoretically because we don't have, we don't have infinite precision when we're measuring. So here's kind of a quick example. Let's say I have a two-factor experiment with time and temperature as my factor. What I'm going to do is I'm going to set time to 20 and temperature to 300. And I'm going to measure the response. And then what I'm going to do is I'm going to reset time to 20 and reset the temperature to 300 and then measure the response. And I'm going to do that a bunch of times, and I'm going to put all of the responses on a histogram. Well, this is, hypothetically what the response distribution should look like. I can get lots and lots of different values between some low and some high. Okay, and ideally we'd like these to be bell-shaped here, or at least approximately bell-shaped after transforming. Now, binary data, okay, it's a response that can take one of two outcomes. So in other words, I can't measure a bunch of different values in some lower and upper bound. It's either one thing or the other. So let's say I have this experiment where I'm only varying one factor, which is pressure. Okay, so I'm going to set my pressure to 200 and see if I get a 0 or a 1. Then I'm going to reset my pressure to 200. I'm going to see if I get a 0 or 1, and so on. Then what I could do is I can make a histogram of the response distribution, which looks something like this, where roughly 2/3 of the time I should observe a 1 when I set the pressure to 200, and about 1/3 of the time I should observe a 0. Now, we say 0 and 1 here. This could be anything. This could be yes, no, it could be pass, fail, it could be blue, green, whatever. But typically the convention is to use 0 and 1 to denote the two possible outcomes, where usually 1 is the outcome that we're interested in. So some examples that you might run into. In quality engineering, we have pass-fail data all the time. Okay. In pharma, a subject either survived, or a patient either survived or didn't survive. There's nothing in between here. You can measure whether after some treatment a disease is present or a disease is absent. Again, there's nothing in between. In marketing, people spend lots of time experimenting and designing ads. So they try to change where they put the advertisement and what color it is and what size it is and what it says. And then all they're measuring is just whether somebody clicked on an advertisement, okay, or didn't click on it. And there's a bunch of other examples that I'm not gonna go through, but hopefully you get a general idea of what's going on here. Now, an experiment may have both continuous and binary responses. Now, when I say binary here, I don't mean proportion. Okay, I mean 0 or 1 for each run in your experimental data plan, in your design. Okay, sometimes what people will do to get around the 0, 1 is they'll, basically make a large batch and compute a proportion. This is, you've one subject gets assigned to a set of factors, and there's either a 0 or 1, so they're all independent. This isn't like a batch that gets converted to a proportion at the end of the day. This is all independent 0, 1 data. And we sometimes say that a binary response is called a categorical response because it takes, it's a category, yes, no, and so on. So some interesting features of binary data. Well, typically we use binary data. At the end of the day, what we're doing is we're going to be estimating a probability. So given that your temperature is this, your pressure is that, what is the probability we're going to observe what it is that we're looking for? Okay. Now, unfortunately, binary data, it's far less informative than continuous data. Okay. And in fact, there was a study done in the 1980s that shows that if you discretize data, in other words, you start with continuous data and you kind of turn it into binary data, because maybe it makes things easier, maybe it makes more sense intuitively. That's roughly, that's equivalent to throwing away about 40 to 60% of the actual data you've collected. In my experience, I actually think it's a little bit higher than this. But anyways, it's a significant chunk of data. So kind of just one little preview tip here is that because, binary data is not as informative as continuous data, you're generally going to require a design that's much larger, compared when you have binary data than you would if you had a continuous response. Okay, so that's kind of one thing that should be pretty obvious, is that if you have, each piece of data gives you less information, you're going to need to collect more of it. So another tip here is if you do have continuous data, analyze it as continuous data. Now, if at the end of the day you need to make a 0 or 1 decision, choose that threshold and kind of make that 0 or 1 decision after you've analyzed the continuous data. Don't turn your data into binary data and then analyze it as binary if you're starting with continuous data. Okay, you're going to get a more informative analysis if you analyze continuous data and then later figure out some threshold where you need to make a yes, no, or a 0, 1 decision. Okay, why are probabilities? This is kind of just a little toy example to really hammer home the point about why binary data is not informative. Well, why are probabilities hard to estimate? Well, let's say that I have a manufacturing process and I want to measure the parts defective. And in reality, that proportion is actually 0.67. So if I ran, a million parts, I would get a proportion of 0.67. That's, we're trying to estimate that quantity. However, maybe I can only sample 5 parts. Okay. If I sample 5 parts, I can get a total of 6 responses, basically 6 sample proportions. I could get 0, 0.2, 0.4, 0.6, 0.8, 0.1. The true probability is 0.67. It's mathematically impossible that I get that exactly right with only 5 parts. In the base case scenario, I could get 0.6, which is going to underestimate the true proportion by about 7%. And that, and I'm only going to do that well about a third of the time. The remaining 2/3 of the time, I'm going to do far worse. And obviously, if you sample 10 parts, things will be a little bit better. You could get a 0.6 or a 0.7, which is pretty close to 0.67. And this occurs about half the time. The other half the time, we're going to do worse. So there's kind of an extra layer of measurement error, in a sense, thrown in when we're looking at binary data. Okay, up to this point, if you've only looked at continuous data, you've probably used the tool called ordinary least squares, as I mentioned at the beginning, to analyze it. Now, this tool is not adequate for 0, 1 binary data. Typically, binary data would be analyzed using a tool called Logistic Regression, and this is actually a new feature to version 12 of the Design Expert software. About a month or so ago, Sherry Kraber gave a What's New in Design Expert 12 webinar, and she gave a preview of Logistic Regression. So if you want some more tutorials on basically the functionality, you could go ahead and check that out. This is more about the practical aspects of actually using logistic regression and designing experiments, knowing that you're going to use logistic regression. So what is logistic regression? Well, with continuous data, okay, we would have a 2-factor interaction model would look something like this. A response, it's a function of some intercept, factor 1, factor 2, and then the interaction of the 2 factors. And we would, condense that to X transpose beta. Now, as I said, this model is not good. It's not well suited for binary data, except maybe in a couple situations, which I'll mention later. So what we do instead is we actually model the probability of success at the ith run, that's what this PI is, with a model that looks like the following. PI is, well, it's that linear model here. So you see this linear model here, but instead what I'm doing is I'm plugging it into basically this logistic function, 1 over 1 plus the exponential of, negative x transpose beta. And you might think, oh, well, that looks complicated. Why would I need to do that? Well, I'm going to show you right now what this looks like. So let's say I had one factor that had 5 levels. So 0, 1, 2, 3, 4. And at each level of the factor, I did some number of independent replicates. So again, independent 0, 1s. These are not proportions. And these were all done in a random order. So what I could do is I could plot the data here. And I apologize, I guess this is a little small, but you can see that I have 9 failures at the lowest level. I have 7 failures at factor at the first level here and 1 success, all the way through 12 successes at the high level. So this is what the linear logistic model looks like here. Okay. So notice here, there's a couple nice things. Well, first of all, the model is always predicting a probability that's between 0 and 1. If I fit just a straight line through this, I'm probably going to get something that looks like this. Okay, I get kind of a nice smooth increase, a nice smooth transition as I go from 0 to 1. Now you might say, I don't think this, I still think ordinary least squares is the right way to go. So what if you did use ordinary least squares? Well, let's say you just fit a straight line to the same exact data. That's what you end up getting here. So what you end up seeing is, first of all, you get a bunch of negative probabilities here. Second of all, you get a bunch of probabilities above 1 here. Okay? And you get kind of a pretty straight shot increase here. You might say, well, you know what? I'm going to get more creative and I'm going to fit a cubic model. So I'm going to fit, all the way up to the x cubed term. Well, that kind of looks like this logistic function here. Okay? But I'm still getting a bunch of probabilities that are negative. I'm still getting a bunch of probabilities that are above 1. So that's one problem. But there's another problem that a lot of times people kind of just ignore. And I'm going to talk about this right now. Precision and p-values and power is something that we all care about. If you fit binary data using ordinary least squares, are you going to get the right precision? Are you going to get the right power? Remember, ordinary least squares assumes that you have basically bell-shaped residuals. Well, it's kind of hard to do that if you could only have a response that's 0 and 1. So here is that cubic ordinary least squares model. Okay, so notice how basically I just took the curve here. The blue lines are 0 and 1 and 0. So notice here, this orange line now, I've put the confidence bands on this plot. So notice here how I get a bunch of nonsense. Okay, here I get a bunch of nonsense. And what this graph is telling me is that I have lots of uncertainty at the, near 0, 1. And I have the most certainty near the middle because that's where the confidence bands are most narrow. If I look back at the logistic model and put the confidence bands on there, notice how, first of all, everything makes sense mathematically. Everything is between 0 and 1. But notice here how this model is telling me that I have the most certainty at the endpoints, and I have the least amount of certainty in the middle. So basically, I'm getting the opposite inference here. So if you were to generate confidence intervals, they'd probably be quite incorrect if you used ordinary least squares, even if you were able to figure out some polynomial model that was kind of a close enough approximation to what it is you're looking for. So that's one thing that a lot of times people overlook, and many times people end up getting, sometimes people end up doing too many runs because they're near an endpoint and this ordinary least squares model is telling them they have a ton of uncertainty. Sometimes they do too few runs if they're in the middle. So just to kind of wrap up this comparison and start moving into the examples, ordinary least squares regression and logistic regression are going to give reasonably close predictions, okay, meaning the lines are going to be similar, when the probability is between 0.2 and 0.8. So if you look kind of in the middle section of all of these graphs, you'll see that some of the graphs are probably reasonably close to one another. Not exactly, but maybe good enough. However, logistic regression is always going to work. It's always going to give you a result that makes sense mathematically. And even if ordinary least squares and logistic regression models give reasonably close predictions, the standard errors, p-values, confidence intervals, and hence maybe the conclusion you reach, the inference, might be very different. So our tip is use logistic regression to analyze binary data. Don't try to, take a tool that you know and love and try to force it into a situation that's not appropriate here. So that's just that's just an FYI. So, and this is just an FYI, just so that you're aware of this. There's other types of categorical responses you might encounter. For example, you might say, well, why only 2 responses? Why do I have to only have a binary response? What if I have 3 responses, like, I don't know, yes, no, or maybe? I mean, I'm just making this up, but you'd have a multinomial response, which is a categorical response, but instead of taking one of 2 values, it can take one of many values. And these are modeled using multinomial logit models. So one common example is a discrete choice experiment where somebody might get, educated on some sort of product, and then they go to, to choose one of 5 brands, and the response is which brand they chose based on the educational information they had received beforehand. And it would be brand A, brand B, brand C, brand D, and so on. So this would be a discrete choice experiment. You could also see a count response. This is semi-related, so something that's like a 0, 1, 2, 3, 4. So it's a whole number that needs to be at least 0. So something like how many times you need to pull the string to start up the weed whacker. That's obviously going to be a 1, 2, 3, 4, 5. This would be modeled using Poisson regression, which is already in version 13. Another example would be the number of defects on a metal sheet. It could be 0, but it's got to be a count, and it needs to be a whole number. Okay, so now I'm going to go through 2 examples here. So hopefully that gave you some information about what the nature of binary data and how we analyze it. So our first example, it's a 1-factor example just to keep things simple. The next example will be a 5-component mixture. But this illustrates, kind of a number of interesting features of binary data. So this is an aircraft fastener manufacturer is, making these fasteners and wants to study, basically how much load can these fasteners withstand. So one factor was varied, which was load, and that went from 2,500 psi to 4,300 psi. And what they did is, they had a bunch of different fasteners that were tested at 10 different loads in the factor range. So what they would do is they'd make a fastener, test it, make a fastener, test it, and so on. Make a fastener, set the load, see if it passed or failed. Make another fastener, set the load to something else, check if it passed or failed. So they actually did this 690 times. And this is the experimental design that they used. Now, like most of these case studies, they didn't actually say why they chose 690 fasteners to test, why they made 690 fasteners, why they tested 50 at the lowest force, why they tested 100 at a force of 2,900. That information actually wasn't given, but this is the design that they used. They used about 10 different forces, equally spaced between the low and the high. Okay, and then they did a bunch of replicates, independent 0-1 replicates. So a new fastener and the load reset. So, there's fastener to fastener variability. And even if you set the load to 4,300 psi, in reality, it might not reach at exactly 4,300 psi. So there's lots of independent sources of error that go into each run. And this is, the number of failures was recorded. So again, these were all 690 runs were done in a random order. Now I did put the proportion failures here, just so that you could see that, well, obviously as force or load goes up, the probability of a fastener failing also increases. Don't actually analyze your data using, proportions, because this, you're basically turning a 690 run experiment into a 10 run experiment. Okay. If you made a big batch of fasteners and all of them, so they're all basically equivalent fasteners, and what you did is you put them all under the machine at the same time and tested the load, that would be closer to a proportion response. But if everything's being done independently, this is a binary response. Okay, so again, just to kind of hammer home that example, because lots of times people are confused about, well, am I doing a proportion? Am I doing 0, 1? This is binary data, but we could still look at the proportion just as more of an exploratory data step. So what they did is they fit a linear logistic model to the data using forward and backward auto selection. So they tried both and got the same model. And this is the coefficients table here. So those are those coefficients that go into that logistic, into that logistic equation. So you see you have intercept load, these are the two coefficients, and so on. So once you're at this point, basically things are the same as they are when you have ordinary least squares. And this is what the model actually looks like with the confidence bands drawn in. So they didn't really say much of exactly what they were looking for, but you could see that, for example, at 2,500, I have fewer than, I'm expected to get fewer than 20% of fasteners failing. At the highest load, I should be around maybe 75%. And of course, you could actually see what the confidence intervals are around those probabilities here. Okay. Next example here. So this is a mixture experiment with actually two binary responses. So this is a chromatography example. So when we have a compound and we want to separate out the mixture, we would use chromatography. Now, ultra high performance liquid chromatography is quote unquote the gold standard for these techniques. But it's very expensive because it requires a very expensive piece of equipment that actually provides the ultra high pressure. What they did in this case is there was a research team that basically tried to find a method that was cheaper but worked, as well as this gold standard technique. So what the research team is trying to do is to create a column that will have a pore size and a skeleton thickness that achieves the same efficiency as this ultra high performance liquid chromatography technique, but with a lower pressure and hence a lower cost. So here's the problem. Well, a formulation does not always create a polymer that's completely solid, which is called a homogeneous column. So for this to work, we need the column to be homogeneous. Also, the pores are not always interconnected, meaning the compound will not flow through the column. The compound needs to flow. So the immediate goal is to design an experiment to model how the blending properties of water, monomer, surfactant, initiator, and so on affect the probability of creating an acceptable column, one that's both homogeneous and capable of flowing through the column. Okay? Column is either homogeneous or not. It either flows or it doesn't. So these are 2, 0, 1 responses. Okay? And this is the actual setup for the experiment. So nothing new here. There's 4 components that are varying. Salt is also in the mixture, but it's always fixed at 0.8 weight percent. And there's also another ratio constraint here on the ratio of initiator to monomer, so D over B, just to make sure that things work out. Here's the design that was built using Design Expert version 12. Okay. They were expecting quadratic nonlinear blending, so they designed for a quadratic model. With 4 components, you need at least 10 runs. They added an additional 10 model points, and they added an additional 40 space filling or lack of fit points. Now, the reason I'm going to talk about this later, why they added those lack of fit points, is because they're going to fill the space well. And when we have binary data, we've noticed that it's often very, very good to have a space that's covered well rather than, say, using replicates. And I'm going to, again, talk about this a little bit later. And there are 2 responses that they measured, homogeneous and flow. Both were yes and no. Now, at this point, the analysis is almost the same as it is in ordinary least squares, so I'm not going to spend really any time on this so I can get to the DOE part, but you could see that 3 of my components are on this triangle plot. The 4th one, initiator, is basically the trace component. So these 4 plots correspond to 4 values of the initiator. Okay, and you can see that the red zone is the zone of high probability of homogeneous columns. Okay, for flow, same thing. And then when I do the joint optimization, I try to figure out where I can get a mixture that gives me high probabilities for both. And here is one location where that happens. And on the ramps plot, I get that water should be 72.15, monomer should be 25, surfactant should be 2, initiator should be 0.05, which gives me probability of a homogeneous column of 97% and a probability of flow of 90%. Now notice here how 2 of the components are at their extremes. So one thing you might want to do is, in a follow-up experiment, consider allowing monomer to go higher, consider surfactant, consider allowing surfactant to go lower. Okay, and kind of the last thing you can do is you can take that solution that's here and check the confidence intervals, because you might run into surprises. At this optimal solution, the probability of getting a homogeneous column is about 0.968. But the confidence interval goes from 0.74 to 0.99, so that lower bound of the confidence interval is actually quite low. And for flow, it's even worse. The probability of flow is 0.90, okay? The confidence interval is 0.48 up to 0.989. Okay, so this confidence interval is incredibly wide here. And again, it's because we're using binary data, which doesn't give us much information. So a tip here or suggestion would be to consider doing additional follow-up runs, but only do them in a region around this optimum. Okay, you don't need to do runs where you know you're not going to get a solution now. And this will hopefully improve your precision and give you a little more confidence about this. In fact, what I probably would have done in this example, if I had been at the, involved at the beginning, is I probably would have done 30 runs in this first stage, kind of figured out where's my maximum likely to occur, and then what I would have done is I would have shrunken my design space and put the remaining 30 runs near that region of interest. So hopefully whatever solution I get far narrower confidence intervals than what I do in this one-shot approach here. Okay, so to kind of, start wrapping things up, here are some practical tips and tricks that you could use if you're doing this on your own. Now, this is a recap of what we've discussed so far. So, tip, a binary response is generally going to give you, it's generally going to require more runs compared to an equivalent design with a continuous response. If you have continuous data, analyze it as continuous. If you need to choose a threshold to make a 0-1 decision, do this after the analysis, not before. Okay? And finally, use logistic regression to analyze binary data. Don't try to force an OLS model to 0-1 data. Okay? So now let's go through some issues here for the DOE portion of this. So here are some issues. Well, first of all, building designs for binary data is generally a pretty hard problem, okay? Well, first of all, binary data is less informative than continuous data. Okay, so if you just open up Design Expert or whatever software and just choose one of the canned designs like a central composite RSM or a simplex lattice mixture design, these are almost certainly going to be too small for binary responses. Okay, optimal designs are also more tricky. So when you build an optimal design for a continuous response, you generally get one optimal design. It doesn't depend on the noise. It doesn't depend on what the true model actually is. But optimal designs for binary data depend on the actual values of the regression coefficients, which of course are unknown. So it's like you need to know the true regression coefficients to build the best design. But the point of building the design is to try to estimate the regression coefficients. So it's this kind of, circular dependency where you don't really know where to start. And unfortunately, this is still an active research area. So experimental designs for binary data is an active research area. There isn't one single, it's not a solved problem, unfortunately. So, every once in a while, I'll still, when I go to conferences or look at publications, I'll still see new methods and new techniques that people come up with. Okay, so I'm going to pick on the optimal designs first. So for a continuous response and linear model, a d-optimal design minimizes this determinant here of the variance-covariance matrix. Now this d depends on sigma squared, which is the noise, the process noise, but we typically assume that this is constant everywhere. So basically this d optimality score is proportional to x transpose x inverse, the determinant of that. Now notice how here in this function, we don't have any beta. We don't have any sigma squared. We don't have any n. We don't have any really parameters in there. X transpose x is only a function of the actual runs that we're going to be doing in the experiment. So this optimal design is going to be d-optimal for basically all sets of regression parameters. And an I-optimal design and an A-optimal design would, the exact same story would hold true. There's only one optimal design. There's only one A-optimal design that we generally care about. Okay, now an optimal design for a binary response and a logistic regression model, this is what the d-optimality score looks like. It's x transpose w x inverse. The determinant of that, this is the variance-covariance matrix of the regression coefficients. Now, unfortunately, this W matrix contains probabilities, which are a function of the true regression parameters. Okay, so it's kind of a tough situation here. So here's kind of a really cool example, which was done in the mid-90s, where Chipman and Welch tried to create the d-optimal design in a bunch of different scenarios and wanted to see how similar or how different they would be. So suppose you're interested in, you have a binary response, you have two factors of interest, and you're interested in fitting just this linear logistic model, so we're not worried about interactions. They built a bunch of 12-run designs for several combinations of the regression coefficients. So beta 1 and beta 2 both being 1, 1 and 3, 3 and 1, 3 and 3, and so on. Well, here are the actual d-optimal designs. If both regression coefficients are 1, 3 points are going to be put at each corner. 3 runs are done at each of the extremes here. Okay. If one of the coefficients is 1 and another one is 3, well, the design looks something like this. 3 runs are, there's still going to be 4 unique runs, but the runs are now not put at the corners. They're kind of, they're arranged in this way. And the runs are kind of jittered here. These should all be on top of one another. They just move them around a little bit so you can see the replicates. But notice how this corner is empty, this corner is empty. Same situation if you have 3 and 1, except it's just, it's this design here, but it's rotated. Okay, so the space looks something like this. Finally, if both regression coefficients are 3, in this case, the d-optimal design has 6 different runs and 2 replicates basically at each of these runs. So notice how there's absolutely nothing going on here, nothing going on here. Okay, so notice how this design here at the top left and this design here at the bottom right, these are both very, very different. Let me go ahead and just clear this up. These are both very, very different designs here. Okay, so could make a big difference. So some practical guidelines. Having some idea of what the regression coefficients are beforehand is obviously going to make life a lot easier. There are Bayesian methods out there that reduce the dependence of the design optimality on the regression coefficients. So they kind of try to do okay in a bunch of different scenarios. Space filling points are very useful because they avoid numerical issues, and also they kind of try to guard against the worst case scenario. So if you had built a space filling design, meaning you just put, one run, kind of, space the points equidistantly, you'd probably get a design that's, in all cases decent. And what we really think is the key is sequential experimentation. So what you could do is, if you are going to be building these designs d-optimally, do a pilot study first, meaning, take a third of your run budget and do a pilot study just to get a rough estimate of the coefficients. You might want to redefine your space based on the results of the pilot study. You might want to shrink your space or expand your space. Okay. Then what you could do is you could take those coefficients from the pilot study and build the full experiment. Afterwards, you can optimize, you can check the confidence interval widths and add runs if you want more precision. So, often we get a question asked as, oh, how do I do an FDS plot in logistic regression, with binary data? Well, if you're going to be using logistic regression, unfortunately, that FDS is also going to depend on the true regression coefficients. So we think starting small, iterating, modifying things and so on, and kind of going over and over and over until you get a result that looks good is the way to go. It's more efficient use of resources, and we've typically seen better results with this in practice. Okay, so just to wrap this up, so some conclusions, some take-home points here is that binary data is usually analyzed using logistic regression. Don't try to force familiar methods to binary data. Take some time to learn the proper tools, and this is easy in Design Expert 12. Don't, I'm going to say this one more time, but don't turn continuous data into binary data. And finally, choosing a design is tricky. So start small and iterate until you achieve your desired results. You might need to tweak a lot of things. You might need to go back to the drawing board, but if possible, if you can experiment sequentially, it's generally going to give you better results, and it's going to use your resources much more efficiently. So some future developments that are coming in Design Expert. In Design Expert 13, we'll have some tools for classification. So lots of times people want to predict, whether something's going to be a 0 or a 1. So there's going to be, confusion tables like this one. There's going to be cross-validation. There's going to be ROC curves and so on. So you could actually figure all this stuff out, as well as a couple other features as well. But this is kind of the big tool that's coming soon in Design Expert 13. Now, Design Expert 12 has only been out for 4 months, so this will probably still be, a while, but it's coming. Here are 2 references you could use if you're interested in logistic regression. This Hosmer-Lemschau book is kind of the Bible of logistic regression. It's applied logistic regression, but it's mostly focused on the analysis of binary data. Okay. There's also this categorical data analysis book by Agresti. This is also kind of one of the classic textbooks. It spends a good chunk of time on logistic regression, but it also talks about multinomial and Poisson and a bunch of other topics. Now, I went and tried to search for books on designing experiments for binary data, and I was able to find this. Okay, in fact, I wasn't able to really find one single good reference. I found a bunch of books that were on design and analysis of experiments with binary data, but 99, maybe like 90% of the the material was on the analysis, not on the design. So, and nothing that's really accessible at the practitioner level, meaning something an engineer could read or something that a chemist can use. It's mostly pretty academic stuff. Okay, so hopefully something comes out later that we could refer you to. So that takes us to the end of the presentation. So I want to thank you all for joining. And again, my name is Martin Besner. If you have any questions, feel free to send me an email afterwards. I'm going to go ahead and wrap up this webinar here in just a minute or two. And of course, we'll have this available on our website, slides as well as the video. So if you want to go through this again, you're more than welcome to take a look. So with that, I want to thank you again for joining us. Hopefully you found, you got some useful information out of this, and hopefully you'll join us in the future. So thanks again. Take care, and bye-bye now.